As a heads up, Chapter 8, especially the back half of Chapter 8, tends to be one of the more difficult things we do this semester. In particular with Chapter 8, place where I see students struggle is there's a lot of vocabulary notation that becomes really important, especially in the back half of this chapter. So, please kind of keep that in mind. I'll try to make sure I'm pointing out specifically like what's going on and why is this important and why you need to be cognizant of this symbol or that symbol or whatever and what the differences are. But you guys really need to make sure that you're being attentive to that stuff that's going on, or else this gets kind of overwhelming rather quickly, just as a heads up. Okay? So in Chapter 8, we're going to be talking about 2- and 3-dimensional vectors. So some of us have heard about vectors before in previous courses. Some of us maybe not. Either way, it's okay. We're going to start as if you know nothing. So we're going to start just with a definition. So a 2-dimensional vector is a quantity that actually has 2 parts to it. It has a magnitude part and a direction part to it. And there's several different ways that we can kind of represent one of these vectors. So the first is with a drawing, or like geometrically. So when we draw a vector, typically we're going to draw an arrow. We refer to that end of our vector as the tail end, and this end of our vector is the head end. The length of that vector is equivalent to the magnitude. And then the direction for our vector, typically what we're going to do is kind of embed an XY axis there and describe the direction as that standard form angle made by the vector. Okay, so our picture is essentially the length is the magnitude and the way it's pointing is the direction. Another representation would just be just listing the magnitude and direction. You know, for example, maybe we had a plane that's flying at 250 miles per hour at a bearing of, 105 degrees or something. in this case, the speed there was representing the magnitude, and the bearing would be representing the direction. And we've seen problems in first semester where we had things like this, right? I think we did some navigation story problems that involved things that you could think of as vectors. And the last representation here, or at least initially, is going to be this component form. So the way we represent a vector in component form, well, when we name our vector, we're going to put that little vector hat on top of it. That's like half of an arrow there that I've drawn. That symbol's to indicate to you that the quantity that you're talking about is a vector quantity as opposed to like a variable, which would be a real number. And we're going to use these wedged brackets to represent a vector in component form as opposed to like a curved bracket, which would represent a point. So that's what a component form vector would look like. Now, typically when we say component form, what we really mean is like the standard representation of a vector in component form. And when we say that, what we mean is that the tail of the vector is at the origin, and the head of the vector is at the point AB, the same as its component. So when we say component form, really we're saying this, is that we're talking about a vector whose tail is at the origin and whose head is at the point represented by that component form. So a little bit of extra notation. So magnitude, the way we're going to represent the magnitude of vector v is with these two vertical bars around vector v. Now you'll notice that it's like, wait a tick, Mr. Kulik. We've used vertical bars for a different symbol before already, haven't we? Well, sure, right? In fact, we've used the vertical bars twice already to represent different operations. But it's okay, because what type of object, mathematical object, those vertical bars are surrounding tells you what they mean. So if we put the vertical bars around a number, that means absolute value. If we put the vertical bars around a matrix, that meant the determinant. If we put the vertical bars around a vector, that means magnitude. So you really have to be paying attention to what those vertical bars are surrounding, because there's no such thing as the absolute value of a matrix, and there's no such thing as the absolute value of a vector. Okay? So again, the symbols here that we're using to communicate make it very important. Also, keep in mind that when we talk about direction, if I draw this vector and I draw this vector, those vectors have opposite direction, right? They're meant to look parallel. I think I did a pretty good job making them look parallel. So we know that the angle that we'd form would be the same, except the arrows are pointing in opposite directions, right? So the way the arrow is pointing does matter. Everybody cool with that? And that should be obvious if that's a direction, right? If I say go this way or go that way, that definitely means two different things, whether I'm pointing forward or backwards, right? Okay. What we want to do next, we have these three different representations. We have the picture, we have magnitude and direction, and we have this component form. What we want to do is talk about translating back and forth between these different representations. So the first thing we'll talk about is going from a graph to the component form. So from the graph, I should be able to read off coordinates for the head and the tail of my vector, right? Pretty obvious that I can do that. So this is my vector v here. The component form for vector v is going to be x2 minus x1, comma y2 minus y1. Sometimes we call that the head minus tail rule. I've abbreviated head minus tail as HMT there. Because what you're seeing is we're subtracting the x-coordinate of the head from the x-coordinate of the tail, and the y-coordinate of the head from the y-coordinate of the tail. What is that really doing? Well, from a geometric perspective, it's causing a translation of that vector. It's moving it, some direction left or right in x1, and then some direction up or down by the amount y1. So basically all it's doing, it's picking up that vector and moving it so that the tail's at the origin. Notice that when we pick up and move that vector, putting it into component form, the magnitude isn't changing. The vector is the same length. And the direction isn't changing. Just the location of our vector moved, right? But it's, it didn't rotate at all. It just picked it up, moved it somewhere else, so the direction stays the same. The magnitude, the length stayed the same, right? Okay. Let's do, next we'll go component to magnitude and direction. So let's say that our component form vector is just AB. Remember when we drew our graphical representation of a vector, we said that the length was equivalent to the magnitude? Everybody's okay with that? And I can calculate the length of something in the Cartesian plane, the xy coordinate system, by just using the distance formula. Everybody's okay with that? So in component form, I remember that, well, I remember the distance formula is the square root of x1 minus x2 squared plus y1 minus y2 squared. So in component form, one point is the origin, 0, 0, and the other point is the head, or in this case, AB. So here, I'm just going to have x1 minus x2 squared plus y1 minus y2 squared, or it just boils down to square root of a squared plus b squared. What's that look like to you guys? Pythagorean theorem, right?
So we could just use that because the zeros will never change.
Yep, the zeros in component form, the zeros are always the same.
Okay, gotcha.
Yep, so we're always assuming that the tail is at the origin. So we're really just a squared minus, or square root of a squared plus b squared.
Is there a situation where the tail will not be a 0, 0?
Nope, not if it's in component form.
Gotcha. So it's only for component form.
Yep. Again, component form to magnitude and direction, right? That's the title. So here, let's say that this is the picture of my component form vector V. Everybody's cool there? So my direction then is going to be this quantity theta, right? So this looks very much like a first semester problem, right? So we're going to name that angle that's made by our vector and the x-axis is alpha. In this case, then I can say theta is going to equal 180 minus alpha. And just like we had in first semester, alpha is the absolute value of y over x. In this case, that would be b over a. And remember here that what you're adding or subtracting from is represented by the part of our angle alpha that's on the x-axis. And then we can tell whether we're adding or subtracting by which axis was the last axis theta passes. So again, if the last one is vertical, we're subtracting. If the last axis is horizontal, then we're adding. Since 0 to 360 describes every possible direction, we would never be interested in finding an angle measure that's negative or that's bigger than 360. All of our answers here for direction would simplest put be between 0 and 360, so don't ever make it harder than you need to. Not that those answers are incorrect, but like, why? You know what I mean? Which always, again, makes life much easier if you're just looking for like one spot on the XY axis. Instead of having to worry about spinning around and making sure it's between blah, 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 or going the opposite direction, everything's switching, or this is kind of the easiest possible scenario, right? Okay. And then let's go from magnitude and direction to component form. So let's say we have some vector v, where the magnitude we're just going to write as, with the vertical bar notations, and I'm going to call the direction theta. So to put that into component form, magnitude times cosine theta, magnitude times sine theta. Does that look familiar? We did that when we did those navigation problems back in first semester, right? When we were getting ready to add the two planes together or whatever, the two plane segments together. We did that kind of thing. First, really what we were doing was taking a vector and converting it to component form. But we didn't even know it. Yep. As an aside, this process here of converting magnitude and direction into component form is sometimes called resolving a vector. So let's do a couple of numeric examples here. Actually, before that, let's point out one little thing. Notice I didn't have an example of going from like the picture to magnitude and direction. Why not? Because I would just go from the picture to component form and then from component form to magnitude and direction. That's really easy to do. In fact, it'll probably be easier than trying to go directly. So let's do that, right? Cool. And then there's no, we also didn't talk about going from component form to the picture, but that's obvious because in component form, the tail is 0, 0, and the head is just the definition. So like there's nothing really to do there.
Just kind of like look at it.
Yeah. Yeah, there's nothing really, I mean, there's not much to do, so I didn't bother to state either one of those two things. Everybody's cool? Okay. All right. So let's say that we have, oops. No, my pen stopped working on me. Pen, come back, there you go. Okay. So let's say we have the vector xy, where x is the point 3, -2, and y is the point 5, 1. And I want the component form. So that's pretty easy. It was just we did that head minus tail rule thing. But which point is the head and which is the tail?
Oh.
Jackson?
X is the tail and Y is the head.
Good. How can you tell?
Because of the little arrow symbol above.
So the symbol on top of my vector is telling me the head and the tail. Very good. Everybody cool with that? Again, the notation matters. There are a ton, right, Amy?
So depending on which way that symbol would be applied, like
If it was pointing the opposite direction, then they would be the opposite things would happen.
Okay.
Yep, very good. Okay, so we do head minus tail, head minus tail. Feel good there? Ain't nothing to it, right? The arithmetic is super easy. So let's say we have the vector u in component form -2, 5, and we want to find the magnitude and direction. Well, the magnitude is pretty easy. That's just square root of a squared plus b squared. So the square root of 29. I'm happy with that. You guys good there? I guess you make it a decimal if you wanted to. I don't really care though. 5 point, I don't know, 3 maybe. Me ballparking. Now if I want the direction then, I'm going to plot the point -2, 5. And I'm looking for that angle, correct? So there's my alpha. That part of the x-axis is 180. Now I just type that bad mama jamma into my calc. I'm not going to bother doing the absolute value on my calculator. I'll just do that in my head. It's way too many buttons to put the stupid absolute values in there when I can just drop the negative sign myself without really having to do much. But I get 111.8 then for my direction. We happy with that? Again, this one may be kind of complicated, but the most complicated part was something we've already done before a bunch of times, right? Which I'm okay with, right? Like anytime we can recycle stuff we've already been doing, that's a good day. Okay, so let's say we have the vector u with magnitude 5 and direction 224, and we want to get the component form for u. So write our wedges, and then just magnitude times cosine of 224, magnitude times sine 224. If I go and I type that into my calculator, that's about -360.60, comma -3.47. Real easy. So we've got these three representations for vectors. They all kind of have their strengths and weaknesses. The two that we primarily will use the most will be component form and then magnitude and direction. Now, the advantages of magnitude and direction is often the magnitude and direction has like some real world ease and measurability. Like these are things that are easy to measure in the real world and often have like meaning in the real world. However, the component form, the advantage is it's way easier to do calculations with things in component form than it is with things with magnitude and directions. So more often than not, the pattern for doing a vector problem is starting with your magnitude and direction, convert that into component form, do all your calculations, take your answer and convert it back into magnitude and direction at the end to report your answer. Well, it's not so bad. It's just we're going to convert it to make the arithmetic easy, do the arithmetic, and then convert it back to the same form you started with. Is kind of the idea for more often than not what we're doing. But the big takeaway here is that the component form is the place where it's really easy to do the calculations. And that's the place where when we talk about vector operations, which we're going to do next, everything we're going to be talking about is in terms of component form. So when we say operations, we're talking about stuff like addition and subtraction and jazz like that. Before we can define any of those things, we need to identify a couple of special, or well, at least at this point, a special vector. That is the zero vector. And the notation we use for the zero vector, what letter do you suppose we use to represent the zero vector? We use the O.
Oh, I was right.
Why the O?
Because it looks like a zero.
Because it looks like a zero, man.
Wow.
So the zero vector in component form is just 0, 0, which means it has magnitude equal to 0 and no direction. This is the only vector that doesn't have a direction associated with it, is this zero vector. But that's okay. We have, with just like the real numbers, we have 0 is kind of a weirdo number also, because it's the only number that doesn't have a multiplicative inverse, right? Like the multiplicative inverse of 2 is 1/2, but the multiplicative inverse of 0 doesn't exist, because if you tried to do 1/0, that's undefined. So, not surprising that the zero vector is also a little weird.
It also doesn't have an opposite.
Well, it's its own opposite, but sure. So the next thing we'll talk about is vector addition and subtraction. So if we say we have the vector u in component form u1, u2, and the vector v, which in component form is v1, v2, then the vector u plus the vector v is just going to be the vector u1 plus v1, u2 plus v2. Really intuitive, right? And if we're subtracting, it's the same idea. This is one of the big advantages of doing things in component form, is like the arithmetic becomes really intuitive. How do you add two vectors? Well, you just add the components together, or the corresponding components together. It's pretty easy. Just as an aside, geometrically, what does this mean, or what does this look like? So let's say we have the vectors u and v here. What we would do to add them is we would just take one of the vectors and place its tail at the head of the other vector. Everybody cool with that geometrically? What's going on there? Now looking at these two addition examples, do you think vector addition is commutative? Does it matter whether you're doing u plus v or v plus u?
Yes.
No way, right? If u1 and v1 and u2 and v2 are just real numbers, you can add real numbers in any order you want and still get the same thing. If I draw this picture, if I drew v first and then drew a, or I'm sorry, and then u, I'm still ending up at the same spot, right, when I connect them. So again, doesn't matter. The big takeaway here in our picture, though, is that when we draw this addition, we're drawing the vectors head to tail. Everybody okay with that idea? Now, we've talked about addition and subtraction. The next thing that would be obvious to talk about is multiplication, division. Well, it doesn't exist between two vectors.
Yes.
But there is a kind of multiplication that exists.
No.
It's called scalar multiplication. And scalar multiplication exists between a real number and a vector. So if I do k times the vector v1, that's k times v1 and k times v2. I'm sorry, what? That's is an element of the real numbers. Those are the symbols that we've talked about. So this is like the real number symbol. This is like is a member of the set symbol.
Oh, okay.
Right? Amy, what's up?
To clarify that last line, I was saying k times the vector.
Yep. So k times the vector. Right? Very important that the k, no hat on top of it. Should be clear that's a real number. The v has the hat on top of it. Should be clear that's a vector. Real number times vector, you just multiply the components by the real number. So let's just do a couple of quick arithmetic problems. Oh, before we do this, though, I want to mention one thing real quick. So I'm just going to finish writing this down. But geometrically, what does scalar multiplication look like? If this is vector v, what if I wanted like 4v or something? And just stacked one on top of another, right? What should make sense, right? If you did v plus v plus v plus v, you'd say, oh, that's 4v, right? That's intuitive. Cool there, everybody? Just to give you a geometric idea of what this is doing. So let's go back to this numeric example. So let's say I'm doing u plus 2v. So what order should I do things here? What should I do first? What do you think? I have two operations going on, right? I have addition and scalar multiplication. Which one should I do first?
Multiplication.
Yeah, same order of operations as what we've done before. So let's go ahead. I might as well write it down. Less likely to make a copy error if I have it right in front of me. So 2 times v is 14.6. If I add those together then, negative 2 and 14 is 12. 4 and 6 are 10. Well, 4v, not much to do there. That's 28 and 12. See, 5v, that's 35.15 minus, and then, well, let's think about it this way. I'm going to think about it just like plus a negative 3. I think that's easier for me to not forget to do the negatives in both places. Let's do it that way. You guys okay with that? I hope so. So I'd get 41.3 then. I always fear that I'm going to not remember to subtract the second set of components or whatever if I just wrote that as a subtraction problem. You know what I mean? You can see yourself doing that, I'm sure. Either way of doing it is fine. I just went and did it that way because, well, that's know your weaknesses. You know what I mean? It's like, oh, that's a mistake I would make. Let's not go that direction so I don't give myself the opportunity to make that mistake.
Okay.
Yeah. Another very important vector is called the unit vector. When we say it's a unit vector if and only if the magnitude of that vector is equal to 1. So how many unit vectors do you suppose we have?
I'm going off what I know, I'm going to guess.
I think you should know, but you can guess too.
But didn't know anything? I would say 4 or 3.
There's more.
8.
More. Yep.
Yeah, let's go.
Infinitely many. Well, Mr. Kulik, how in the heck are you getting infinitely many? Recall the unit circle, right? The length, or I can describe any point on the unit circle as cosine theta, sine theta, right? And what's the distance from the origin to any point on the unit circle? 1. Everybody agree? It's a unit circle centered at the origin. And in fact, then that describes a component form vector whose head is on the unit circle. Since there's infinitely many points on the unit circle, I have infinitely many unit vectors. That's it. It's pretty neat. Unit vectors turn out to be real important because they're essentially like a direction vector, because I can use them as a proxy for the direction of my vector, because if it has magnitude 1, if you combine it with something, you know. Anyways, so here's a question. Can I take any vector and find the unit vector in the same direction?
Probably can't. I really guess.
Yeah. So here's what we're going to do. I'm going to calculate the magnitude of v. And then I'm going to multiply my vector by the reciprocal of its magnitude. That's it. Wait, whoa. Mr. K. That seems too easy. Why is that? How do I know that the magnitude of u is 1? Well, let's just check it here, dudes. Sound good? Since the magnitude of v is just a number, I can pull that outside of the magnitude, right? That's just 1 over the magnitude of v is just a scalar, so I can pull that out. And the magnitude of v is just magnitude of v, which is just 1. So, oh, okay. Yeah, no doi, Mr. Kulik. No doi. What do you guys think? Okay there? Should we do a numeric example? So suppose we want a unit vector in the same direction as the vector v equals 5, -6. Well, start by finding the magnitude of v. So 25 plus 36 is square root of 61. So then my unit vector is just 1 over the square root of 61 times 5, -6. I'll do that scalar multiplication. And then I guess I'm going to rationalize my denominator. Might as well. There we go. We could always check this as well, right? So again, I'm just going to do the magnitude formula. So I have a squared plus b squared I get 1. So I'm pretty confident I got that. Just checking, you know what I mean? Showing you how to check your work. Since it's all numeric, it's usually easy to do that. You know what I mean, guys?
So it should always equal 1.
If you want a unit vector, its magnitude better as heck be 1. Okay. So infinitely many unit vectors. That's nice. We know how to take any vector and turn it into a unit vector. That's nice. Now there are 2 unit vectors in particular that are of interest to us. They're called the standard unit vectors. we abbreviate them as I and J. And they're the two most obvious unit vectors you have. I is the vector 1, 0, and J is the vector 0, 1. And the nice thing here about these unit vectors is they unlock a new representation for a vector called the linear combination representation. So if I have the vector CD, I can represent that as the vector C0 plus the vector 0D. Everybody cool with that? Obviously, if I add those together, I get CD. Yeah? And on the vector C0, if I factor out a C, I'd have the vector 1, 0. And similarly, in 0D, if I factor out a D, I get the vector 0, 1. Maddie?
I also need it.
Okay.
Amazing.
So our linear combination form for the vector CD is just C times the vector I plus D times the vector J. Note that C and D are scalars and I and J are vectors. Okay. Next up, we're going to define a fourth vector operation today, right? Addition, subtraction, scalar multiplication. Yep. Fourth operation, which is called the dot product. Nope.
Yes.
So if we have the vector u, represented by u1, u2, and the vector v, represented by v1, v2, we'd say the dot product between u and v is the product of u1 times v1 plus the product of u2 times v2. What looks weird here? When I look at that dot product formula, both items on the left-hand side are vectors. And what's the result of the right-hand side?
I don't see any arrow.
It's a scalar.
Yeah.
Yeah.
Wow.
So the dot product is always going to just give you a number. No vector, just a number. We'll do some numeric examples here in a moment, but before we do that, I just want to go over a couple of properties for these dot products. Probably we should say no, I think it's okay if it's 0 still. That's only one. Yeah, that's fine. Okay. So we're not going to prove any of these properties because that's actually part of your homework assignment. But the first dot product property is that the dot product operation is commutative. That is, u dot v is equal to v dot u. The second, the easiest one that you'll have to prove is the multiplicative identity property, that the zero vector dot any vector is just equal to 0. We have the distributive property. Oops. There's the scalar multiplication associative property. And the last one is called the magnitude property. Says that any vector dot itself is equal to the magnitude of that vector squared. Yes? It's just a W.
Oh, but for the distributive property?
Yep.
Not like all these things together.
Oh boy. All right, let's do some numeric examples here. So u dot v, so that's going to be u1 times v1 plus u2 times v2 or just negative 17. Uh-oh, w dot v, but w's in this weird linear combination form. What should I do? Just write it in component form? right? So what does that look like? State 4, right? The I is just the x component, the j is just the y component. So that's easy. So what do we have? We have 8 times -1 plus 4 times 5. So -8 plus 20 is 12. Okay. So according to the associative dot product property, or the scalar associative property, I can multiply that 5 into the w, or I could multiply the w, or do the dot product for the u and w first, and then multiply the answer, or 5 to that answer. That's kind of what I'm going to do. So I'm going to do 5 times w1 times u1 plus w2 times u2. So that's 16, and then times 5 is 80. And then -12 times 5 is -60. So I get 20. That okay with everybody? On D, I'm going to do this way. Clearly, I have to do u minus w first. But as long as I'm doing u minus w, I might as well do 2 times v. You know what I mean? So I got 2 minus 8, which is -6. And then 4 minus -3, which is... I'm sorry, u minus w. So I have -3 minus 4, that's -7. And then 2 times v is -2 times 10. So I have -6 times -2 plus -7 times 10. So I have 12 minus 70, or -58. My z's have a bar in the middle. I think it's probably a 2. That's a z. That's a 2. That's just me knowing that I have terrible penmanship and I can't tell a z and a 2 apart.
Okay. Same thing happens with me when I try to write a number 5 versus writing an S.
Yeah.
Manuscript.
Ugh. My 5s and
sloppy 5.
yeah, my 5s and s's I can tell apart. My 2s and my z's not so much.
I was told I had a horrible habit of making my A's look like U's because I'd never closed the top. I would curve it but I wouldn't really close it all the way.
Sometimes that happens to me, but not all the time. Sometimes, but not always.
So the next thing we want to talk about is the angle between two vectors. So if I have some vector u and I have some other vector v, we're talking about this angle between the two of them. So this is can be a confusing looking formula. What is that symbol there that I've highlighted in yellow? That's a dot product. What's this symbol that I've highlighted in green? That's multiplication. On top, the dot between two vectors means dot product. On the bottom, the dot between two magnitudes, a magnitude is just a real number, is multiplication. So again, wanting to be clear about the notation, what's going on, how you can tell the difference between what kind of dot are we talking about, right? Because that matters. No, it's because it's two magnitudes. The bars around it bars around the vector means magnitude, and magnitude is just a real number. So it'd be like 5 times 7. When it's written in a formula like this, it's really easy to get confused at what you're doing, right? If you actually put the numbers in the places for things, it'd be like, oh yeah, cos. Yeah, so just a number times a number. A vector dot vector, you know. I'm going to skip the proof for this. It is in your, it is in the lessons or whatever if you wanted to take a look at it. It's basically just using the law of cosines. But let's say we want to find the angle between 7, -6 and 2, 2. So there's 3 things I'm going to need. I'm going to need to do the dot product with u and v. I'm going to need to do the magnitude of u. Uh, 49 plus 36 is 85. And then the magnitude of v. So 2 squared plus 2 squared, that's square root of 8. Notice that I'm not bothering to reduce those radicals at all. I acknowledge that they can be reduced, but I don't really care because I'm just plugging them into a cosine inverse anyways. So it's not like they're in my final answer, so why would I bother to reduce them? Similarly, I'm not bothering to rationalize the denominator there because, again, I'm just taking the cosine inverse of that stuff. So, like, it's not going to appear in my final answer anyway, so I'm not going to waste my time. Everybody so far so good? Oops. What did I do there? So when I do that, I get 85.6 degrees. Again, pretty easy to do formula. You just have to kind of keep in mind what you're doing. Everybody's cool? I want to point out to you real quick here, from a geometric standpoint, since we're using cosine inverse in this formula, and the range for cosine inverse is always 0 to 180, the angle between the two vectors that you're finding is always going to be the smaller angle. So for example, if these are my two vectors, I'm going to be finding this angle and not this one. It's always going to be finding the smaller angle. Now, for the most part, if all you're doing is using the formula, like, it doesn't really matter, this point that I'm making. But if you're drawing the picture and going, does this answer even make sense that I got? You have to keep in mind that you're finding the smaller of the two angles between the two vectors. Always the one that's between 0 and 180. Okay. Last definition here for today. and it's this term orthogonal. We say that the vectors u and v are orthogonal if and only if their dot product is equal to 0. When we say orthogonal, what do we really mean? It's like a kind of equivalent to perpendicular, that the angle between them is 90 degrees. So if I just ask you to show if, say, these vectors are orthogonal, all I'm going to do is take the dot product of the two vectors and show that they're 0. And I'm done. Pretty easy problem, right? All you have to do is do a dot product and you know what the answer is supposed to be. That's it for today. At this point, you guys should be able to do 1 through 40. Now, is that going to go into this Sunday's homework check? Nope. Next Sunday's homework check. For this Sunday, the only thing you have to do is the Chapter 7 review. But there are a lot of problems in this chapter. I would not want to get too far behind, so I would try to have these 40 done by the next time we have class, just FYI.